this week. We had great lectures today with John and Andres, which made my task very difficult because I cannot compete with them. And also I really enjoyed talks of the students about configuration spaces of graphs. Amazing. So what I prepared is mainly general talk about topology in robot motion planning. And at the end of my talk, I will mention some new results. But most of my talk will be kind of results which are known, especially for people, many people who are here. So I apologize in advance. So the goal of robotics is to create autonomous robots. So we hear in the news, we hear about self-driving cars and different autonomous machines. So this machines and systems, robots, will operate autonomously, so they will know what to do, and so the tasks which they obtain from us should be very short and clear, and how to implement the tasks, they have to decide themselves. They have to know, they have to have algorithms how to perform different tasks. So one of such tasks is what is called motion planning problem. So it is when we have a system which needs to be brought from one state to a different state. How it is performed, the system must decide by itself. So when we say state, if I think of myself as a system, so my state is not only my position in this room, but also how my arms are, elbows, different angles. There are many parameters which determine my state. It's not only two-dimensional, two parameters determining where I am in this room. Actually, my state involves many parameters. And this algorithm, so suppose I am in this state now, like this, and I want to come to this microphone, so I come here. So this is, I make this motion, and without thinking, I automatically do it. So how do we know? I mean, it is a complicated sequence of motions. We want this ability to be available for robots, for machines.
Michael, all these parameters, they shouldn't be all independent. They should really impose some kind of restriction of the range they can move, right?
Yes, okay. Exactly. So these parameters are not independent. Mm-hmm. So our, because it will be clear.
Okay.
It's absolutely right. Parameters are not independent. So our configuration space, which we will discuss a bit later, is not a flat space. It is some manifold. So, but now we are discussing what is motion planning algorithm. So it's a method how, let's say, system will move from one state to another. And a simple example of such system is this Waze. Yes, when you introduce in your car your destination, but the car knows where you are because it gets this satellite signal. So in fact, the car knows the initial state where it is now, and it knows, well, you tell it where you want to go, right. And then it provides you with a route. Mm-hmm. And in fact, sometimes it gives you several options to avoid, let's say, tolls and highways, and it may provide you several options. So this is a motion planning algorithm. Yes, so we will discuss in this talk algorithm of this type, but high-dimensional spaces. So when not only two parameters where you are matter, but so now let's talk a little bit about what is the configuration space. It's exactly what you mentioned already. So we have mechanical system, let's call it S, and we have has variety of states, which we call field X, and this is one letter called the configuration space of our system. So usually a state is determined by finitely many parameters, maybe many, but finitely many. So angles, different lengths. So we obtain a vector. We can say a state is determined by a vector with many coordinates. And if we take all such possible vectors, we obtain some subset of Euclidean space. And this set represents all possible states of our system. This is called the configuration space. So because this configuration space naturally comes as a subspace or Euclidean space, it has topology on it, it has a structure of a topological space, so we can speak about continuity of motion. And in many problems, we don't need to know the system. We just, if we know the configuration space, we can analyze the behavior of the system just knowing what is its configuration. I'm not saying for all purposes, but for certain purposes, it's enough to know the configuration. And in this talk, we will see that once we know the topology of our configuration space, we will predict character of instabilities of the behavior of the robot, knowing the cohomology algebra of the configuration. So this will be later. This will be So a simple example of system of type is called robot arm. So it consists of certain number, finitely many bars connected by revolving joints, which looks like that. And each bar can rotate, so it has an angle. But each bar can be position of each bar can be determined by an angle, which it makes, let's say, is a horizontal direction. And therefore, the configuration space is the product of the circles. So this S1 is n times S1. Each S1, it is a circle which parameterizes angles, point on. And this is if our robot arm is planar on the plane. But if it is in R3, then each bar has two-dimensional degree of freedom. So position of orientation of every bar is determined by a point on two-dimensional sphere. So then we have our configuration space will be the product of yes. Another example is the following. So suppose we have some space Y. You look at points, n points, and a different number of points lying in Y, and we assume that they must be distinct. They shouldn't collide. So this is an example of restriction when they are not independent. They are dependent because they exclude that one particle is in the same position where as a particle. This is actually an example when of particles on a graph, it is this type, configuration space of this type. So it is denoted by F, Y, N, and so we can think of a system. In this case, we have N objects in our space Y. Y is ambient space. It can be just Euclidean space. It can be RC. We can think of, let's say, many planes flying the sky, and the only condition is that we don't want them to collide. So this is the configuration space in this case.
But we can have the two objects at the different places but at the same angle. Then the other one of the Y will be the same.
Well, if they have the same angle, it's okay, but not at the same point.
Yeah, that's right.
Yeah.
So therefore, that n-tuple should be a subset, right? It's not a full space, right? Y1, Y2, Yn.
Oh yeah, I mean, all n-tuples satisfying this condition.
Mm-hmm.
Not all n-tuples,
Not all
n-tuples with this property.
Right.
With this property.
Okay.
So this is how it looks on this. So what is motion planning problem? I just want to rephrase it in mathematical terms. So we have a system, and we look at the configuration space of our system. X, the points of this space X are states of our system, and motions of our system entered by curves, by maps of unit interval into X. This parameter here is time. So when time starts from 0, we are here, and then the point moves, and time 1, it arrives at state B. So motions of our system are such paths in our configuration space, and we will assume that our space is path connected. This means that any 2 points can be connected by a path. But if it is not path connected, we just take the component of the space, because this means that there are 2 different kind of parts of our configuration space which are not really related. So an algorithm, a motion planning algorithm, is what we want to put in the computer of this system. So it should take as input pairs of A and B, where A is the initial state, and B is the desired state, the state we want to get, our system. This is input, as an output should be a curve or continuous motion of our system, which starts at this point and ends at that point. So now we just want to rephrase this in different terms. We consider, we denote by x to power I. So I is this interval 0, 1. X to power I means the space of curves in X. There's topology, it has a very good, very convenient topology, which is called compact open topology. And on this space, we have a map which associates with every path. With every path gamma, we associate 2 points, the initial point and the end point. And this map is, so we look at all paths, all motions of our system. And so these are all motions of our system, and these are pairs of states, And this map P associates with every motion, with every gamma, associates this pair, gamma at 0 and gamma at 1, the initial point of the path and the final point of the path. It's not what we want, it is what we have. Not an algorithm. So what is an algorithm? What is motion planning algorithm? Motion planning algorithm is a map which goes in the other direction. It goes from x cos x to x to power I. And this map should satisfy this property that if we apply S, and then we apply P, the previous map, then this is an identity map. I just want to show you this again. So we have this map P, and S is a map, this algorithm is a map this direction, such that if we apply S and then P, get identity, we are in position. So it means that with every point, with every pair of points A and B, we apply S, we obtain a motion, and this motion starts at A and ends at B. So this is what in topology it is called section. Section. So section is a map goes in the other direction. So in effect of this is kind of our vibration, and section goes this way. So section goes in opposite way. So we want to have a section, and every section is an algorithm, is a motion planning algorithm. This is what we want. And we ask, do continuous motion planning algorithms exist? And the answer is the following. So they exist if and only if our space is contractible. Continuous motion planning algorithms exist only when the space X. And it's quite easy to see. So if we have a motion planning algorithm, let's say S, have a motion planning algorithm, then for every 2 points A and B, we can apply S, and this will be a path which starts at A and ends at B. So if we fix this endpoint, keep it fixed, and we vary A, so if I apply to A1, I get this path. Take A2, I apply this path. Take A3, I get this path. So I obtain a continuous way of collapsing all my space into this single point. So this is exactly what is called contractible. And vice versa, if my space is contractible, so if I can collapse all my space continuously into one point, then I can just show it here. If I want to go from, let's say, from A1 to A3, then I apply this trajectory, come to B1, and then I reverse this, go to A3. So if I can continuously get from any point A to a fixed point B, then I can get from A to any point.
So the section is just the reverse of this contractible, right? If it's contractible, then you reverse it.
Yes.
Then you
yes,
can go to.
Yes,
then you have a section.
Yes, exactly.
Gotcha.
The continuous section exists if and only if our space is contractible. So now this question about how restrictive is this assumption? How maybe all configuration spaces are contractible and fine. But this is exactly this topic which is called universality theorems for configuration spaces. So This universality, there are many universality theorems, type of universality theorems, and they always say that the spirit that, operation spaces are not special. Anything, any space, well, any reasonable space you can realize by a mechanism. You can create a system which will imitate this space, which will have this space as its configuration space. And type of mechanisms or type of systems which are usually considered, these are called planar linkages. So these are very simple mechanisms. But planar has bars, and these bars are connected by joints, and some vertices of this mechanism are fixed on the plane. We will see a few examples. So, for example, this is one famous example of a linkage. This is called Poiseuille linkage. So this is famous because it allows to transform circular motion to straight line motion. So here you see this point move around the circle, and then this point will move along the straight line. So, well, of course, there should be some radius here so that it makes it circular motion. Circular motion is very easy to realize because you just fix one point and it's a circle. So this point B moves along this red circle, and point Z along red line. You can read about this in this classical book, Hilbert Confucian. This linkage had a very important role in history of civilization, I would say, because it allowed, it was a problem when steam engines were constructed. Well, steam engine, you need circular motion here, straight line motion here. And there were many attempts to do so. And Poiseuille linkage was a perfect solution. Before this, there were some solutions which were not perfect. There was some approximate. It was not really straight line. It was approximate line. Okay. So this configuration spaces of linkages is a classical subject. What is important is that any linkage generates configuration space which has the structure of a real algebraic variety, because this can be described by equations, polynomial equations with real coefficients, like distance equals 1. Like x1 squared plus 1 squared plus something is 1. This exactly describes a circle. There are many equations like this. So they have this structure, mathematical structure, which is called real algebraic variety. And one of these theorems, which is very old theorem from 19th century, which is called Kempe's universality theorem, says that if you take any real algebraic curve on the plane, you can construct a linkage which will draw this curve. So not only straight line you can realize, but any curve given by polynomial equations, for any curve you can linkage will draw this curve. And one of the ways of stating the theorem is the following, that there is a linkage which signs your name. So Kempe was Also, he kind of gave a proof of four-color theorem, but it was false. In fact, once he was president of the London Mathematical Society. This is one of the theorems, the universality theorems, proven by Jordan and Steiner. It says that any compact, connected, real algebraic variety is homeomorphic to a connected component operation space and a linkage. So you see that there is no perfect correspondence. I mean, there's connected component. It would be better to remove this. And then here is another theorem, which was proven by Topology and Nielsen. And it says that if M is a smooth, compact manifold, then there is a planar linkage whose configuration space is diffeomorphic to a disjoint union of a number of copies of M. In here, I mean, there is something which needs to be improved, but at the moment it's not done, so latest. So what does it mean, discontinuity? How does it affect the behavior of our motion planning algorithm? Well, discontinuity means that we will have some pair of initial finite configurations such that very close to this can perturb it slightly, and the algorithm will produce a very different motion, completely different. So here the motion is this way, perturb it slightly, motion will go this. For example, suppose I want to go from here to O'Hare Airport, and from here to O'Hare Airport. So I put in GPS and it tells me that way. And then I moved just 1 millimeter and I put it again and it tells me completely different. I mean, it's a little bit strange, right? So, this is discontinuity. This is discontinuity. So our questions are the following. Can we measure this discontinuity? Appear in motion planning algorithm. Can we minimize them? Given that discontinuities are caused by topological properties, configuration spaces, one asks which topological or homotopical properties are mainly responsible for discontinuity. So, I mean, you will see what I have in mind. I mean, we will come to this. We will see that these cohomology algebras of these configuration spaces can be used to estimate this and measure them. Okay, so what we want to do is we want to introduce numerical invariant, which is called TCX. So TC stands for topological complexity. It is a measure of navigational complexity of given space. And roughly, this TCX is the minimal number of continuous rules which are needed to describe any motion planning algorithm. So this workshop which we had in this week is exactly about this TCX, about different versions of X when you have symmetry and fractions and so on. So to define this, we do the following. So I want to construct a motion planning algorithm, and I don't know if it exists a continuous, globally defined motion planning algorithm. So what we do, we split our space X cross X into a certain number of sets. They are all disjoint. They have nothing in common. They all cover the full possible set of pairs. And on each of them, we have a continuous section. This S is a section. So this motion planning algorithm is a section, so restriction of this on this Fi is also a section, and now the condition is that it is continuous. And there is a last property which we will just ignore for now. I mean that each of the sets must be what is called ENR, but let's just no, it doesn't matter. It just to avoid some pathological spaces. So what is important here is how many these sets we have. I just want to emphasize that I start from 0. So it is just, yeah, this is, yes. So I just wanted to emphasize that motion planning algorithms which appear in practice are usually of this type, because the sets Fj. So how this is done in practice? It says if some angle is less than pi, go this way. If this angle is greater than pi, do that way. So I mean, you have some inequality, most likely polynomial inequality. Then you implement continuous motion. So usually the algorithms which appear in practice are tame. This is the definition of what is called tame algorithm. And now we come to the main definition. So we say that the topological complexity of a tame motion planning algorithm is the minimum number of domains of continuity. Yeah, the minimum k for which we have such a definition. So it may happen that the same algorithm you can implement with one partition of x cross x and with some other partition of x cross x. And then this is our main definition, is that the topological complexity of a path-connected topological space X is the minimal topological complexity of motion planning algorithms in X. The notation is DCFX.
Topological complexity or continuous. Continuous.
Well, tame motion planning, but what is continuous?
Fi.
Each Fi is an arbitrary set.
But our height should be continuous.
Section. So a restriction of the section on Fi is continuous. This here is continuous. So this is a number which we associate to a space. And these are three kind of basic properties of this number. So the first property is that it is a homotopy invariant. So it is a really good fact because it means that if you change your space by deformation or retraction, the space this number doesn't change. It also means that you can compute it easily. So it doesn't depend on small details of your space. It depends on local properties. Second, it is equivalent to this lemma which we had before, that it is 0 if and only if X is contractible. Number 3 is upper bound by dimension of X cross X. So CCX cannot be bigger than the dimension of X cross X or twice the dimension of X. For example, if my configuration space has dimension, I don't know how many, let's say 20 angles, 20, so my TC, my complexity will be 40. But if I want to control 100 planes at the same time without collisions, then it will be 100 times 3 times 2, so it will be let's look at this example. I think I'm going too slow now. Go faster. Let's look at this example. So our space is a circle. So as a first, and we want to construct a motion planning algorithm on the circle. So as F0 and as this set F0, we can take all pairs MV which are not antipodal, so they're not opposite to each other on the circle. And if they are not antipodal, then we can move from A to B along the shortest geodesic arc connecting these 2 points, and this motion is continuous. Right, so this is our first set F0, and on F0 we have a continuous section. Now the remaining set is F1, so the set of antipodal points. And here, if we have 2 antipodal points, we can fix some orientation of the circle once and for all, and move A to minus A along this orientation. So this gives another section, another motion F1. And this shows that this complexity of the circle is 1, because it is less or equal to 1, because we have a tame algorithm with 2 sets. So it is at most 1, but it cannot be 0, because 0 would mean that it is contractible, but the circle is not contractible. So it is 1. Now, if we can take a similar approach, suppose now space is a sphere, Sn, of 4th dimension. We can take F0 the same as before, the set of all pairs which are not antipodal, and F1, again, the set of all antipodal pairs. Now we can use the fact that n is odd, so we have a non-zero tangent vector field on the sphere. We can use it follows, so we can move from A to minus A. I'm sorry, I don't have a picture here, but we can take this tangent vector at this point and move along this tangent vector along the geodesic curve from A to minus A. Because this vector moves continuously, we obtain a continuous section. So we see that TC of Sm is also 1 for n odd. But if we take an even dimensional sphere, for example, S2, that S2 is 2-dimensional sphere, then we don't have this. So this we still have the set of 0, the same, but F1, I mean, this here we don't have a section because we don't have a continuous tangent vector field which is never 0. So it must vanish somewhere. We can make such tangent vector field which vanishes exactly at one point. Let's suppose it vanishes at point A0. Then we can take for F1 all such antipodal pairs where A is distinct from A0. Here on this set we can define our motion as before, moving along the geodesic tangent vector EA. This geodesic curve comes to minus A. And then we have remaining set, which consists of a single pair, A0 minus A0. So we see that the topological complexity of even dimensional sphere is 2, is less or equal than 2. But in fact, it equals 2. I need to, 1 second, need to, I'm just thinking, I need to jump a little bit. Yeah, we need to. So if we look at configuration space of n particles in Rd, so this is what we discussed earlier, that they should fly and no collisions. So for example, it is exactly like in your talk. So we have A1, A2, black particles, A1, A2, A3 somewhere, A3, A4, and here we have fine. So this is initial configuration, B1, A2, A3, and B1, B2, B3, B4. This is our final configuration. So we want to have an algorithm which will move black particles into white particles without collisions. So what is the complexity here? So this, it is not exactly the same problem because they looked at graphs. This is in Euclidean space. So actually complexity here is higher than here approximately it is twice the number of particles. It is kind of independent of the dimension of the space. I'll just so now yes, so you see my title was robot motion planning and aspherical spaces. So what I spoke about now is basic material. But now I want to speak about the last 10 minutes. I want to speak about aspherical spaces. So what are aspherical spaces? So maybe I'll just, before I start, I just want to say that there are some results here, but there are some open questions. So it's a little bit mysterious and not resolved. For young people, is. So what is an aspherical space? So a spherical space is a space which has trivial higher homotopy groups. So I of x, 0 for I greater than. So the space has only fundamental group 1. If fundamental group is also trivial, then it is contractible. So this we have no problem with. So we have only fundamental group and this. So here we have examples of spherical spaces. So for example, graphs. All graphs are spherical. All orientable surfaces except also its opposite. Opposite, yeah. Genus greater than 1, greater or equal than 1 are spherical. And also non-orientable surfaces, starting from 2 are spherical. So there are many interesting spherical spaces. because the homotopy type of an spherical space depends only on its fundamental group. So TC of a spherical space will be a function of the group. So we can define TC of a group. As follows: we have a group. We construct for this group a spherical space, having this group as its fundamental group. Such space always exists, and we take TC of it. So these are main questions. So we want to be able to compute TC of pi algebraically. And motivation for this is this famous Algebraic theorem, which says that for an spherical space, the Schnellmann category equals the cohomological dimension of the group. And just to remind you,
normalized.
Well, a category is normalized. I mean, in my topic, is normalized.
Because usually this graduates, this our students use non-normalized.
Yeah, but for me, it's already.
Yes, just
yeah.
avoid confusion. Yes.
Everything normalized. Yeah, restriction and conjugate normalized. So just wanted to mention that homological dimension is kind of the highest dimension where you may have non-trivial homology of your group. So we want to have something of this type, or TC of pi. And let's look at some examples. The simplest example is Zn. TC of Zn is n. And we compare this with homological dimension of Zn, which is n, homological dimension of Zn equals 2n. So in fact, in this case, TC equals homological dimension of the group itself. But now, if I take free group from M generators, when M is greater or equal than 2, then TC equals 2. Homological dimension of the group is 1, and homological dimension of group to itself is 2. So in this case, TC equals homological dimension of the group times itself. Now, another example, if we take a group which is fundamental group of a surface, orientable surface of G was greater than 1, TC equals 4, and homological dimension of pi cross pi is also 4. So in this case also TC equals this number, but in the first case TC was equal to this number. In fact, Yuli has a paper which shows that you can take any number between homological dimension and twice homological dimension, realize it by TC of pi. So there is no general answer in terms of homological dimension pi cross pi. It should be something different. Okay, so this slide, I just wanted briefly to mention our recent paper, reprint with joint with Mark Grant, Greg Lupton, and John Fair, which uses Breton equivalent cohomology to characterize TC of pi. So I will not go into details of this paper. I just want to make it really briefly. So here we E will denote pi cross pi, and EG is a universal classifying space. So it is a contractible space with free G action on it. And this, so D is some certain family of subgroups. D is certain family of subgroups, and EG of G is another classifying space which allows contractible, but it's not free action. It has isotropy lying in this class D, class of groups D. So there is a canonical map of spaces, and what we proved in that paper is that this TC of pi equals the smallest dimension of a GCW complex L, which can be, which can appear in decomposition of this map through L. So this is exact characterization, but it is not an algebraic characterization. Characterization in terms of classifying spaces associated with this group. Later, we also used Breton cohomology to obtain some bounds, lower bounds and upper bounds on TC of pi, but we didn't get to final answer. So here is another result, which is joined with Stefan Mescher, and it is says that have a hyperbolic group, then TC of group is either this number, which is the maximum possible, or this number minus 1. So first of all, here we have kind of two extra assumptions. So first, we assume that our group is hyperbolic, so it's not for every group. And secondly, we have this kind of dichotomy. The answer is this or that. So it has a maximum or maximum minus 1. So in fact, we have only one example when the second possibility happens. It's a single example when pi is Z, infinite cyclic group. In all other known to us examples of hyperbolic groups, we have TC equals maximal. Just want to say, want to leave a few questions. So about hyperbolicity, so hyperbolic groups were introduced by Gromov, and one of Gromov's theorems says that typical group is hyperbolic, so random group is hyperbolic. Random, to produce a random group will be hyperbolic with probability close to 1. So, I mean, there are different models of random groups, and of course, this theorem is valid in some models, but not in all of them. But nevertheless, hyperbolic groups are very important. And, for example, the mental groups of orientable surfaces are hyperbolic for G greater than 1. I think I'll skip this. So this was a definition of, I wanted to give definition of hyperbolic group. So maybe I'll finish this talk by mentioning this conjecture. So this conjecture says that if we have a torsion-free hyperbolic group, no, I made a mistake here. I should have said for any non-commutative,
otherwise Z is example.
to exclude Z, yeah. Z is counterexample, yeah. So for any non-commutative torsion-free hyperbolic group, TC of pi will be this maximum. And I mean, if this is true, this would be a very nice, simple answer, kind of answer, typical group. I think I'll finish at this point. Thank you very much for inviting me. It was great.
Question for the speaker? So he had to leave right away because he's slide was cancelled.
5 minutes ahead.
Okay, but just saying he will not want to be around that long for the key, but I hope everybody is key for half an hour, and so after that we will half an hour.
Vous entendez que tu piensas aí?
Okay, okay.